So fluid dynamics, we are going to learn about streamline and turbulent flow first of all. In order to define the streamline and the turbulent flow, first of all, we have to know about the Bernoulli principle. You already remember this principle, that this principle was stating that like the velocity of the fluid increases when the pressure decreases, okay? When pressure exerted on the fluid decreases, this is going to cause the velocity to increase, okay? So this principle known as Bernoulli principle. So what about streamline flow? Streamline, the other name of the streamline flow is laminar flow, okay? This is a type of fluid flow where the fluid travels smoothly in regular layers. So regular layers means what? Like on a layer of, let's say, on the, how can I say, on the, like a smooth layer, okay? It can be like
airplanes wing.
like on a table, okay?
Okay.
On a table, okay? So the velocity and pressure remain constant at every point in the fluid, okay? This could be a pipe also, this streamline, okay? It could be a pipe. Inside of the pipe, the water can flow or the gas can flow inside of the pipe. So since the layer is regular, it is going, the pressure is going to be constant at every point of the fluid, okay? The second one is a turbulent flow. This type of flow, there is a disruption of the layers of the fluid. It can be like a smooth, like inside of a bowl, for example. Inside of a bowl can be, when you put water inside of a bowl or a balloon, there is going to be disruption inside of the layer, right? When you touch it. So this is going to be turbulent flow, okay? What is the example? Like, for example, inside of a pipe over here on the right side, inside of a pipe on the right side, you can see it. So there is a streamline flow because there is no disruption. That means the pressure is going to be the same for all points. But on the this part, for example, this part, there is a disruption inside of the layer. Okay, maybe something touched the pipe or some other external factors, could be a force effect on the pipe, and this disrupt the flow of the water or gas. Okay, so this is going to be turbulent flow. All right. So this type of flow is chaotic and unpredictable. We are talking about the turbulent flow because it is consists of the irregular eddies, like circular current eddies. You remember eddies from the current, circular currents of the air. These are going to push on the surface of the pipe, and the unexpected things are going to happen inside of the pipe. Okay, so that's why it is chaotic and unpredictable. So factor affecting the streamline flow or laminar flow, there are some factors. There are 4 factors actually affecting the laminar flow. The first one is the density. The second one is compressibility. The third one is temperature, and the last one is viscosity. We are going to learn about viscosity. You don't know about viscosity yet, but you already know about density, compressibility, and temperature. Compressibility like means how much its volume can be reduced. Okay, compressibility, when you compress the fluid, it can be like water or it can be anything like gas. So the density and compressibility of air, important factors at high speeds, because as an object travels rapidly through air, it causes air to become compressed and more dense. Okay, it is going to cause air to become compressed and more dense. So as a result, other properties of the air will change as well. Okay, other properties of the air will change as well. There are going to be more molecules in it. Yes.
How is it going to make?
Okay. So the effect of temperature change on airflow also become important at high speed. Why? Because a regular commercial airplane, think about it, after landing, it is going to feel like it's going to cool down actually after touching the ground. Before that, remember, due to air pressure, due to air resistance, it is going to feel like too much heat on itself. Okay. But when it touches down, when it stops, it is going to feel cool down. Okay. This is because of the temperature of the air and flow of the air as well. Okay. So factors affecting streamline of cars, boats, and planes. There are some factors. Don't forget this part. Object with larger surface area will travel slower through the air. What is the reason? Can you tell me?
Oh, because they have high air atmosphere.
Yes, they have a larger surface area, so they are going to hold too much air. Think about a parachute and a kite. Okay, A parachute is larger, has larger surface area than a kite, so a parachute will be slower than the a kite. Okay, this is because of the air resistance. So there are certain shapes which helps object to speed up and travel faster through the air, other than fluid. Okay, these are called streamlining. These are called streamlining. For example, a plane can recording. Let's continue. So we can summarize this as the total pressure is constant along a streamline. Okay, so the total pressure is constant along a streamline. We can summarize Bernoulli's principle like this. Okay, so let's continue. So there is an example over here. Water flows at 10 meter cube per hour through a pipe with a 100 millimeter inside diameter. The pipe is reduced to an inside dimension of 80 millimeter. Find the velocity of water in each part of the pipe. So the first part of the pipe, in order to find it, first of all, we have to know the cross-section area of the pipe. We're going to use the formula of pi d square over 4. Okay, this is how we are going to find the cross-section area of the pipe in this situation. Okay, pi d stands for the dimension. Pi d square over 4 is going to give us the cross-section area of the pipe. So there is an equation like this: v1 times a1 plus v2 times a2 plus v3 times a2. Whatever, how many velocity we have, we are going to add them. Here we have only one. We are looking for one velocity, so that's why we are going to use one part of the equation. So in order to do that, 400 velocity, 400 millimeter pipe, we're going to calculate like this. Water flow is given us. Okay, water flow equal to velocity times area. Okay, velocity times area. So since it is per hour, we have to convert this one into seconds. So remember, 1 hour is 3,600 seconds. Okay, so we are going to do like this: 10 meter cube per hour times 1 over 3,600 hour per second. As you see here, the hour, they're going to simplify themselves. So here, at the end, we're going to find our velocity as 0.35 meter per second for 100 millimeter diameter pipe. Okay. What about for 80 millimeter? Again, for 80 millimeter, we are going to apply the same formula. So 10 meter cube per hour times 1 over 3,600 hour per second. Again, the hour, they're going to cancel out each other. So time V times area. Area is this time the diameter is 80 millimeters. So we're going to take the 0.08 meter per square over 4. Okay. When we do this, we're going to find the velocity 0.55 meter per second. What does this mean? This means when the pipe, the diameter of pipe gets smaller, the velocity of the fluid gets larger. Okay, this is important, this part. So velocity gets larger when the diameter of the pipe gets smaller. So there is another question here. Use a simplified version of Bernoulli equation to find the total pressure when the static pressure is 5 Pascal and the dynamic pressure 7 Pascal. What are you going to do? You're just going to simply add these two to find the total pressure. Static pressure 5 plus 7 dynamic pressure. When you add them, you're going to find 12 Pascal according to Bernoulli principle. Okay, let's continue. So this part we are going to learn about viscosity. This term, it is a new term that you're going to hear it. What does viscosity mean? It means like the internal resistance of a fluid flow and a measure of thickness of a fluid. Okay, the internal resistance of a fluid to flow and a measure of the thickness of a fluid. This is known as viscosity. So the force required to drive the layers, we're going to have a force over here. So eta times, this eta is going to stand for viscosity times area or times change in velocity over change in in distance from container wall. Okay, this dy stands for distance from container wall. A stands for cross section area. Eta, this is a Greek letter eta. It's not n. Okay, it's eta. It stands for viscosity. Okay, so some liquids, again, let me just go back. Some liquids flow more readily through pipes or move out very freely to allow the body to move through them. These are the liquids that have a low viscosity. Okay, when they have a low viscosity, they can allow the other bodies to pass through them. Okay, so they are very runny, we can say that. What about the coefficient of viscosity? This is important. So thick oil and the like of the thick oils are quite opposite. They are very viscous and large drag forces appear when layers have to slide over another. What does drag force mean? Drag force means the force which resists the flow of the fluid. Okay, the force which resists the flow of the fluid is, it looks like resistance. Okay, you can say air resistance, like drag force could be air resistance. Okay, so the viscosity of a liquid may be measured by a quantity called coefficient of viscosity. Is going to be eta again. So kilogram per meter second is going to give us the unit of the viscosity. So there is Stokes law and terminal velocity. Terminal velocity, remember the terminal velocity? You already remember from unit 5. So the maximum constant velocity reached by falling body when the drag force acting on it equal to the force of the gravity. When the drag force and the gravity are the equal, there is going to be terminal velocity over there. What does that mean? That means the velocity will be constant. The object will not accelerate anymore. For example, when you throw a ball, the ball is going to accelerate till 1 point. When the drag force means air resistance and the gravity have the same value of the force, the ball is not going to accelerate anymore. So it is going to be that velocity is going to be the terminal velocity of the object. So there are 3 factors that affect the magnitude of the drag force. The first one, the size of the body. Okay, a reasonable guess might be that what matter is the area which the shape present to the fluid. But here, this turns out to not to be the case. The force is proportional to the radius. Okay, the force is proportional to the radius. That means the greater the radius, the greater the force will be. The force is also proportional to the velocity at which the sphere moves through the air. Okay, A double velocity means double drag force. 3 times velocity means 3 times drag force. So the third factor is the viscosity of the fluid, which is eta. Okay, the eta. These put them all together, and we get the following formula. This constant, there is a constant which is 6 pi actually. I'm going to give you in the next slide. Times eta is the viscosity constant, times r, the radius of the fluid, and times velocity. This is going to give us the formula over here that we needed, okay? To find the drag force. We are going to use this formula. 6 pi times eta times radius times velocity. This is going to give us drag force. Okay, let's continue. Reynolds numbers, I'm going to pass on the Reynolds numbers part. You don't need to know that. So heat, temperature, and thermal expansion. This is the last part that we are going to learn. So let's define the specific heat capacity. Remember the specific heat capacity from grade 9. Specific heat capacity means the heat energy required to rise of the temperature of 1 kilogram of a body or given substance by 1 Kelvin. Okay, 1 kilogram by 1 Kelvin. This is called specific heat capacity. Remember the heat capacity? Heat capacity was the temperature of a substance by 1 Kelvin. Since this is specific, that's why we take only 1 kilogram over here. Okay, specific heat capacity is specified. So the we use the symbol C, small c, to show the specific heat capacity. So to find the number of joules, we are going to use the SI unit of specific heat capacity, joule per kilogram Kelvin, or joule per gram Kelvin. You can use both of them. This is the unit of specific heat capacity. Second one, we are going to multiply the number of the kilograms or grams that you are heating. And third one, we are going to use the formula here. The energy equal mass times specific heat capacity times delta T, change in temperature, okay? Change in temperature. And when we do this, we are going to find the energy or specific heat capacity of any substance, okay? So let's do an example. The specific heat capacity of water is 4,200 joule per kilogram Kelvin. How much energy will be needed to warm 800 grams of water from 17 Celsius to 27 Celsius? So here there is one thing that you need to know. You don't need to convert Celsius into Kelvin, because even though when you convert it, you're going to see that the change in temperature is 10. Okay, Kelvin or Celsius is going to be 10. So that's why you don't need to just convert the Celsius into Kelvin. You don't need to do that. So to find delta T, we are just going to simply subtract 27 minus 17, which is going to be 10 Kelvin. Okay, and then let's put the others into the formula. We have C 4,200. We have delta T 10 Kelvin, and we have mass 800 gram, which is 0.8 kilogram. When we multiply this, we're going to find the energy required as 33,600 joule. There is another question. This question, this time, it's kind of a complicated question than the before question, because we don't know energy here. So in order to find the energy, we are going to need to find the power, okay? So using a current of 1.5 ampere, a 12 volt heater was used to heat 100 grams of water for 15 minutes. The temperature rose from 21 Celsius to 52 Celsius. That means delta T will be 31 Kelvin. Based on this result, how much energy would be required to warm 1 kilogram water by 1 Celsius? So in order to do this, first of all, we have to find the energy. So to find the energy, we're going to use power times time. And again, to find the power, we have to use, here are given, we have current and the voltage. So remember, power means current times, we can use the current times voltage to find the power. So then, when we put that inside of the formula, we're going to find the energy as 16,200 joule, okay? This 12 is the volt, 1.5 ampere times 15 minutes. Since it's minutes, we have to convert to seconds. That's why we multiply by 60. So it is going to be 16,200 joule. So to find the specific heat capacity from this formula, we can send M and delta T on the other side of the equation as division. So we know the energy again, 16,200 over M is 0.1 kilogram, as you see over here, and change in temperature is 31 Celsius. Since it's asking in Celsius, you don't need to write Kelvin, okay? So then we are gonna find the specific capacity 5,226 joule per kilogram. Actually, it's gonna be Celsius. Okay. All right.
Mr.
Yes.
What's